Hello AP Stats students, this is Mr. Hazelhorst here with your introduction to Chapter 9 and the concept of sampling distributions. As we start this video, I want you to just stop and think about what your answer would be to the question that I have on the bottom of this slide. All right, people with glasses are, fill in your response. Now I know you might be thinking, well, this is kind of a strange question to start a lesson with, but in actuality, this is a great lead-in into where we're going to begin to go in AP Statistics. As you answered the question, people with glasses are, and you filled in your own word, really what you were using is the process of statistical inference to an extent. When we talk about statistical inference, it's the idea that we're going to draw conclusions from a population from sample data. So as you think back to that question, people with glasses are, and you answered your own word, whatever it may be, you haven't seen every single person in the world who wears glasses. You've seen a sample of people, and from that you've drawn your own conclusion, whatever it may be. Maybe you've said they're smart, or who knows what, all right? But whatever conclusion you've came to, you base that off the sample of people that you have witnessed with glasses. And from that sample of people that you witness with glasses, you've come to your own conclusion about the population of glass wearers overall. Now, sometimes in common day language, we refer to this as a stereotype. And in statistical inference, we're not going to make stereotypes. We're going to look at numerical data, and we're going to use that numerical data from a sample to try and draw some truth, a conclusion about a truth of a population. Now, just like your answer to people with glasses are, just because you think that doesn't mean you're right. And sometimes in statistics, just because our sample says that doesn't guarantee that it's right. But over the course of the next few chapters, we're going to learn some processes that are going to give us great confidence in the answers that we come up with. And that's what we're going to begin to build the foundation of today. Again, this idea of preparing for statistical inference with the use of sampling distributions. Let's go back real quick and review some important terms and symbolism that we've learned over the course of our AP Stats course so far that are going to start to be really important as we move into this process of statistical inference. So the terms that we want to review are the ideas of parameters and statistics. Remember, way back in the beginning of AP Stats, we said parameters are numbers that describe the population. Right? Now, in reality, again, we're not going to know those values. Because dealing with an entire population is difficult, all right? So as we define parameters, all right, we use the symbols that we have on the left side of the slide here. We know that mu is our symbol for a population mean. Just the letter P is our symbol for a population proportion, and we know lowercase sigma is our symbol for a population standard deviation. A statistic, on the other hand, what we're going to deal with over the course of this class is we deal with sample data. Again, statistics coming from samples, and this is what we're going to use to estimate whatever our unknown parameter is. All right, so again, our sample mean value is x bar, our sample proportion value is p hat, and our sample standard deviation is a letter s. Now, it's important to know when we talk about a parameter, that is a fixed number. Okay? Again, it's a truth about a population. And that's not going to change. Statistics, however, change based on the sample that we select. If you and I are both studying the same population but choose a different sample from that population, chances are we're going to get different values for our sample mean. Because again, those are estimates. Okay? We're trying to estimate the parameter using those values. And so sample values are not fixed like a parameter value is. So this brings us to our concept of a sampling distribution. And a sampling distribution it's kind of one of those big concept ideas. It's something that's really hard for us to actually create in reality. But it's a concept that all future concepts and topics that we cover in statistics are going to be based on. So when we use the phrase a sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the same population. Now, we've done lots of simulations and we've run lots of different samples but we didn't create an actual sampling distribution. Those were just approximations of a sampling distribution. Again, if we're going to create an actual sampling distribution, we're going to have to look at every possible sample that you could take of a certain size from the given population. Now again, this is a big concept, and it's kind of a tough thing to grasp. So I'm going to try and give you an example through the rest of this lesson to help give you something concrete that you can tie this back to. So let's take a look at that example. So in this example, we have a population of test scores here. All right, I have 10 test scores that we're going to define as our population. Now, this is a really small population. It'd be really easy for us to work with, to analyze. There would really be no need for statistics if this is our population size. But we're going to use this as our example, again, to help give some concreteness to this idea of a sampling distribution. Okay? So this table, again, representing our population. Now, because it's a population and because it's so easy for me to work with, we could easily calculate the mean, and I've done that here. The mean of these 10 test scores comes out to be 69.4. This is a parameter. That's a fixed number. That is never going to change in this population, okay? So the mean, a truth, is 69.4. The standard deviation is 7.63. Again, because that is a population of scores, that's a truth. It's not a statistic. It's a fixed number. It's a fact. All right? Now, what I want us to consider to help, again, give a concrete example to this idea of a sampling distribution is I want you to think about how many possible samples could we create from this population if we were going to select 4 test scores at a time. Now, this would be really easy for us to figure out. This is just a combination problem. If I do 10 combination 4, what I find out is there are 210 different samples of size 4 that could be created from these 10 test scores. All right, so just think about that. One sample could just be the scores 0, 1, 2, 3. One of them could be 6, 7, 8, 9, right? So if I mix and match these 10 test scores, taking 4 at a time, I could create 210 different samples. Now that seems kind of crazy for such a small population, but again, that's the idea of a combination here, all right? Now, if we found every single one of these possible samples and we calculated out the average of each of those samples, and put those together in their own distribution, that is what we would refer to as a sampling distribution. All right? Now, my original plan was to figure out all 210 of these different samples and actually display that for you. And then I got to start working on that, and I realized this is going to take forever. So I haven't created the actual sampling distribution, but I did create an approximation of the sampling distribution. So what I did was not 210 different samples, but I created 50 different samples from this population, and I want to show those to you right now. So here you have 50 different samples of size 4 from those 10 original test scores, and you can see those listed out here. So if you look at each category, I have the group number, I have 4 of the different scores, and I found the average of those on the far right column of each side of this table. All right. So when I look at these numbers here, all right, these numbers, again, if I did this for all 210 possible samples that could have been created of size 4 from this population, if we put all those means together as a set of data, that would be the sampling distribution. Now, I've given you some statistics about these data. Again, they're not parameters down below here because we're not dealing with every possible sample of size 4. We're only dealing with 50 of the 210. So my values down here are not representing parameters. but are representing statistics, all right? So the mean of the means, all right? The average of my 50 averages came out to be 69.36. The standard deviation of these means came out to be 2.441. Now, let's go back and compare those to what the original parameters were. So here's that population with the parameter values. Again, remember our mean, the fixed parameter of this population of 10 test scores was 69.4 with a standard deviation of 7.63. Right? So back to our sample data, notice how close our actual average was to the fixed parameter. All right? If I take all 50 of these means, and notice, I don't think there's a single mean that's listed in either of these two tables that actually has an average of 69.4, which is the true value. We actually have some values that are kind of a little ways off. We look at the number here, 64. I think this is the smallest mean that's in the list, right? That's over 5 units away from the average. And then we have some of these values here, and like 74.5, again, that's 5 values away, but it's 5 values away on the other side. So as we take all of these different samples, right, that are all different, all right, and we refer to that as sampling variability, we recognize there's going to be a difference in our samples. But as we combine those all together in this idea of a sampling distribution, those individual variabilities balance each other out. And what we end up with is a great approximation of what the actual parameter value is. And the reality is we shouldn't be surprised by this. What this builds off of is the law of large numbers that we talked about back in first semester. We know as we increase our sample size and probability settings, right, over time, we're going to have a great approximation of what the true probability is. And that's what we see here, even with our sampling distribution, right? If we wanted to approximate the mean of that 10 test population, we could use this idea of a sampling distribution and get a really close approximation. Now, the other thing that I want you to notice, remember our standard deviation of the population originally was over 7. It was 7.63. But our standard deviation of the sampling distribution is much smaller. It's 2.441. Now, statistically speaking, is that a good thing or a bad thing? Well, I hope you said that's a good thing. All right, we know the less variable our data is, the more closely centered it is. All right, so let's give you an idea of what we mean by this concept of sampling distribution. We've looked at these tables of numbers and seen the mean and standard deviations of it, but let's give you a visual picture of the difference between a population of data and the sampling distribution of data. All right, so what you are seeing here are two normal distributions that have been drawn using the data that we've just looked at. All right, we know in order to create the shape of a normal distribution, we only need to know two values. We need a mean and a standard deviation. Well, this kind of shorter, wider normal distribution that we see here, this is the normal distribution that's used creating the data, the original data of those 10 test scores. So we had the mean of 69.4 and a standard deviation of 7.63. Right? So we have this, again, the mean in the center, all right, and we have a very wide distribution because of our large standard deviation. Remember, the area underneath that normal distribution will be 1. Right? This taller, skinnier normal distribution that we see is the normal distribution that's created using the mean and standard deviation from those 50 samples. And what I want you to take from this picture is a very important understanding that in a sampling distribution, it will be much less variable than even that of the original data. And that's good because what we want to be able to approximate is the center. Well, notice how much more of the sampling distribution is closely centered on the mean than even the original data was. Now, why is that? Well, it's really simple, right? In a sampling distribution, all these outlier, these larger test scores, and if you go back and look at the original test scores, there was a low test score in there was a 58, and there was an 80, and those are kind of outliers compared to the mean overall. But those outliers get balanced out when they're put in a group and averaged together. And that's what leads to the smaller variability, the smaller standard deviation that we see in a sampling distribution. And this is going to be really important as we move forward in statistical inference. So let's talk about a couple of terms that are going to be really important to us in future chapters. So the terms that we want to introduce here are the ideas of bias and variability. All right, when we refer to bias, we're relating to the center of the sampling distribution. All right, if we have a sampling distribution that has high bias, that means it's not very close to the true parameter. If we have a sampling distribution with low bias, that means it's close to the parameter. All right, and an unbiased statistic or an unbiased sampling distribution means that it's equal to the actual value of the parameter. Now understand something, that it's going to be really hard for us to determine the bias because in a vast majority of the situations that we deal with, we're not actually going to know the true value of the parameter. But what we're going to find out as we study this idea of a sampling distribution and statistical inference is that we can feel really good about our bias because of the facts of a sampling distribution. And you'll see that as we work forward in future chapters here. All right. Now, the second term that I want us to be aware of is the idea of variability, and this relates to spread. Right? When we think of the root of the word variability, it's a variable. How much do things change? All right. That's the idea of spread. Okay. So spread is determined by sampling design and the size of the sample. All right. And this is an important concept. All right. Larger samples will always give us a smaller spread. And again, it relates back to that idea of the law of the large numbers. The more data we include, the more those outliers are going to get balanced out, and the closer we're going to center on what our true parameter is. And that's an important concept of sampling distributions, using samples to eliminate the effect of outliers. I shouldn't say eliminate, but to minimize the effect of outliers. Okay? And we can refer to our variability as either high or low. Right? The more spread out it is, the higher the variability. The less spread out, the lower the variability. Now let's give you a visual picture of what we mean by bias and variability. When we think about the concept of statistical inference and trying to estimate the value of a parameter using statistics, we can almost think of it like shooting arrows at a bullseye. Right? The parameter itself is the middle of the bullseye. That's where we're trying to hit. That's what we're trying to approximate, to estimate. We're trying to determine. And so we take all these shots at it using statistics. A statistic is like an individual shot at the target. Right? In this diagram down here, we see an example of what we would refer to as high bias and high variability. All right, remember, our goal is to hit the bullseye, the target. Well, if I look at this spread of shots that I have here, we can see that this isn't anywhere close to hitting the center of the bullseye. And they're also really spread out. All right, so since our center, right, the center of these shots would be right here, right, since the center of these shots is off from the center of the bullseye, that's the high bias. And since those shots are spread out, that's the idea of high variability. In my second target, we see the idea of low bias and high variability. Again, the shots are still spread out, but if I were to hit the center of those shots, well, the center of those shots would hit my bullseye. So, yeah, they're spread out, but even within their spread, they're close to approximating the center of the bias when I look at them as a group. So low bias, high variability. Our third bullseye is an example of what we would refer to as high bias, low variability. Right? When I say low variability, look how closely clustered all those shots are. They're all close together, which is a good thing. The bad thing is they're all closely centered away from the center of the bullseye. right? The center of these shots, again, is going to have high bias. It's not anywhere close to the center of the bullseye. And in our third example, our third bullseye, this is what we actually want to see in statistics, right? We have low bias and low variability, right? This is a great shot at that target over and over and over again. That's consistency. And this is what we're looking for out of our sampling distributions in statistics. And when we have that, we can trust that our estimate, our approximation of the parameter is good and accurate. And that's what we're looking for in statistics. Now again, these concepts I understand they're not really concrete concepts. And so these are just some ideas that we're going to put into place over the course of the next few chapters. I don't expect you to understand them in fully 100% after this short little video lesson. But these are some ideas that we want to begin to think about and see how they apply over the course of the next few chapters. And hopefully in a few weeks, you're going to have a much better understanding of these concepts that we covered today. So in closing, I just want to remind you to make sure you complete the form below the video on my website. Communicate any questions or thoughts that you had from today. And thanks for watching today. I hope you guys are having a great day, a great evening whenever you're watching this video. And we'll see you in class soon. Bye.
Made with Doodlecast Pro.